And on the other hand, the kernel is a special kind of subgroup, which we'll usually use this symbol to denote not just subset, but subgroup. But the kernel is a special type of subgroup, which is called a normal subgroup. A normal subgroup H in a group, and it's denoted this way, not just by the contain sign, but a little triangle. So it means it's better than just a subgroup. It has a nice property. Has the property that if you take any G and G, for all G and G, if you take the conjugates of H, well, GH, G inverse, let's do it that way. That's another subgroup of G. You can easily see that that's closed under multiplication, because if you multiply GH, G inverse by GH prime, G inverse, then these two G's cancel, and you get G times HH prime, G inverse. So this set, all elements of the form G, an element in H times G inverse, is closed under multiplication. So it's another subgroup of G. A normal subgroup is one where this is always equal to H. So we might say, if we call this multiplication on the right by G and on the left by G inverse conjugation, because that's what it is, then we might say the normal subgroups are closed under conjugation. By all elements G and G. It's clear it's closed under conjugation by elements in H. If you multiply an element in the H, an element in the subgroup H on the left by H and on the right by H inverse, that's still in H. But this is amazing that it's closed under conjugation by G. And that's true of a kernel, but not of an arbitrary subgroup. That's a really important distinction. It was first noted by Galois, who I told you developed group theory. So let's check that the kernel is a normal subgroup. It's easy. So if we have an element G in it, well, let's say H is in the kernel. We have to check that GH, G inverse is also in the kernel. So we apply F to it. F of GH, G inverse, using the homomorphism property, is F of G, F of H, F of G inverse. Now the fact that H is in the kernel means that F of H is the identity element. So this becomes F of G times the identity element times, and F of G inverse is the inverse of F of G, which is just the identity element. So that's why the kernel is closed under. Now if you want to see an example of a subgroup that's not normal subgroup, take the following subgroup. So this is just an observation. When you make a mathematical definition, you should always see whether it actually narrows the field or not. Maybe all subgroups are normal. Maybe this property is held by everything. So you have to actually, to see that this is a distinguished character of subgroups, you have to exhibit a non-normal subgroup. Now you can't do that in an abelian group. In an abelian group, this is obvious because G commutes with H. So you can move the G over to this side and cancel the G inverse. So you have to go to a non-abelian group to get a counterexample to a normal subgroup. Can someone suggest a simple non-abelian group to work with? S3. S3. So let's take a look at S3. And let's take a simple subgroup to work with. Let's take the identity element and our transposition tau, where tau sends 1 to 2, 2 to 1, and fixes 3. Okay? Now, I claim this is not normal. So you have to find an element in the group that takes this subgroup outside of itself. Well, let's try something. Let's try conjugation by tau prime, where tau prime is the element that switches 2 and 3 and fixes 1. So tau prime clearly takes e to itself when you conjugate. But what is tau prime, tau prime inverse? Well, tau prime inverse is the same as tau prime. So we're calculating tau prime, tau prime. Well, let's see. If it's this element, we'll be able to tell by just evaluating it on 3. Because this is the unique element in the group other than the identity that fixes 3. So let's see if it's tau or not. So we'll apply it to the element 3. Tau prime of 3 is 2. So this is tau prime of tau of 2. Tau of 2 is 1. So this is tau prime of 1. And tau prime of 1 is equal to 1. So this element does not fix 3. It takes 3 to 1. So in particular, it's not equal to the element tau. In fact, it's the other transposition. It's in fact equal to tau double prime. One can figure that out pretty easily. It has to, we'll see later. Well, I mean, this has to be conjugated into a subgroup, and there are only 3 subgroups of order 2 in this group, generated by e and tau, generated by e and tau prime, and generated by e and tau double prime. And tau double prime is the unique one of these things that takes 3 to 1. Okay? So in fact, we find here that tau h, tau inverse, is the subgroup e tau double prime. And so there's a non-normal subgroup for you. So in particular, that subgroup is not the kernel of a homomorphism. That subgroup is not the kernel of a homomorphism.